this webinar who are interested in Georg's talk. So Georg is from the National High Performance Computing Center at the Friedrich Alexander University in Germany. And we came in contact with Georg due to some papers he and his group published, which we found regarding work on A64FX, which was also in the Okami cluster. And then I contacted them and we started collaborating on that. And they also already gave an amazing webinar about their tools to Okami users. And today, Georg will give a more broader talk about performance modeling. Thanks a lot, Georg, for that, and please take it away.
Okay, thanks, Eva, for the introduction, and thanks again for having me. I'm very pleased to be able to speak in your seminar. So my title, the title of my talk is From Numbers to Insight via Performance Models, and that's one of the main motives of research and also education that we follow in our group, to try to educate people not just to measure performance of programs running on parallel computers and present the performance numbers, but also interpret them in the proper way and to make sense of those numbers in order to get something out of it. So here's a quick overview. I will give you a quick introduction to what we call white or gray box performance modeling, and then an introduction to resource-based modeling with respect to computer systems and how we base our modeling procedures on the resources a computer gives us when it executes programs. And then I will give some details on the execution cache memory model, also on the Roofline model, which is somehow like a specialization of the ECM model. Some of you might have heard of the Roofline model already. And then going beyond the node level, going beyond the socket and the chip, I'll show you how some of the assumptions that you make when going highly parallel about modeling break down. And you have to think in different ways about highly parallel programs if you want to analytically model the performance or runtime of such programs. Okay, so first of all, a motivation and sort of like a definition. What is analytic performance modeling? There are lots of definitions around and people understand different things when they talk about analytic modeling. So for me, analytic modeling means to construct a simplified model for the interaction between the software and the hardware. And what I want to do with that is to understand lowest order performance behavior. Whenever the actual performance behavior diverges from that, I have to correct and iterate, so to speak. So here's some basic questions that these analytic models address. So the first question is always, what's the bottleneck? What's the hardware bottleneck I'm up against? Okay, how does a specific part of the hardware limit the performance? And maybe what can I do about that later when I got the insight? So after optimization, there might be a different bottleneck, and also the model should give me information about that. And also I get info about the impact of hardware features to different extents on the performance of my code. So I might want to use that insight for co-design. How can I build a machine that matches the requirements of my program in the best possible way? Also architectural exploration. Let's tweak the parameters of our machine. Let's find out what tomorrow's machine may look like, or let's put the parameters of tomorrow's machine, which may not even exist yet, but I might know the basic features, model our programs on it and see how it will behave when it runs tomorrow. So one important question is what happens if the model fails? So if my predictions about performance or runtime of a program are incorrect. Now that may seem like a bad thing. Actually, in practice, it's a good thing because we learn something about the problem. And we may, even if it doesn't work, okay, even if it's too complicated to model, and computers and programs are complicated, we may still be able to use the way of thinking in a productive way and in a predictive way. Okay, some of these points will be covered in this talk. So getting a little bit more specific, we group the different kinds of modeling procedures we see in roughly 3 groups. And the first group we call white box modeling. White box modeling uses only documented hardware properties and hypotheses. So I go to the vendor's documentation of my processor, of my compute node, of my motherboard. I look up all the numbers. I look at my program and try to come up with a hypothesis about how they interact. So this is what I call a purely analytic model. No measurements, no phenomenological input is required to come up with a runtime prediction. We call that white box. Okay, everything is open, everything is clear, and no input parameters are hidden or unclear. That in practice, that doesn't work out very well. So I need at least some phenomenological input. One example is the memory bandwidth of a processor. Okay, I might want to measure that because the theoretical bandwidth is one thing I usually can't achieve. So I measure the bandwidth, and that's some kind of gray input. I don't know how that comes about. I don't know why the bandwidth is as it is measured, but I can use it as an input to my modeling procedures. I call that gray box because it's still a model that's based on first principles with some components that are not well explained or not, which I'm not able to explain. And then there's black box modeling. Black box modeling uses measured performance data or speed up data or any data that can be measured on a computer system and some hypotheses about how the program behaves. So for example, I could set up a fit function with parameters that I think describes my program well in terms of scalability. And then I want to fix these parameters in order to get a good description of scalability and extrapolate to larger systems. Okay, that's a different kind of modeling procedure. It can be well automated. There's a lot of work in this direction. How can we automate performance modeling to get very quickly a huge number of performance models? But they're curve fitting, and the kind of insight and use of these models is different from gray box and white box models. So in order to maybe approach some of you who might come from the area of physics, I'm a physicist myself, I want to compare the white and gray box thinking with an example from physics. So if you watch an apple drop from a tree, then after some heavy thinking, you might arrive at some interesting laws of gravitation. Okay, that's like a first principle kind of thinking. And you can do different things with this kind of law. You can combine it with other laws like Newton's second law of motion and come up with a behavior or a prediction of the behavior of an apple falling to the ground on some small scale. Okay, not planetary scale, small scale. And in that law or in that description, we have a parameter g, which we exactly know how to calculate, of course, because we know the law of gravitation and we know the kind of approximations we have to do to arrive at this equation. But it could also be measured. Okay, it could be something that could come in as a measured parameter, and that would make the model a gray box in this respect. And of course, I can do other amazing things like predict the trajectories of satellites and moons. So here we are with first principles models that might also be like might have a little bit of gray box flavor by putting in some measured quantities. Now, if you go to computing, there's a lot of models flying around that have this kind of flavor, this kind of property. You might be familiar with Amdahl's law. Amdahl's law is based on the assumption that a part of your program is purely sequential. It cannot be parallelized. We call that S as a percentage. And the rest of the program is perfectly parallelizable. So the speed up with n workers, CPUs or nodes, would be 1 divided by S plus 1 minus S over n. And then you could put in some communication overhead, okay? Some normalized communication behavior that you may or may not be able to predict analytically. So we want to predict the program speed up. We base it on some assumptions. In that respect, it's a white box model. Okay, I don't have to measure anything. I make assumptions about my program. And then the question is, where does this communication model come from? And for the communication model, I can use another analytic model. I call it the Hockney model for message transmission time. You may also be aware of that. The time it takes to transfer a message is the latency, like a setup time, plus the length of the message divided by the asymptotic bandwidth. That's the time it takes to transfer the message once the first byte of data flows. And you can plug it into the Amdahl's law and then compose these two models in this way. Okay, and then again, these parameters, especially the bandwidth and the latency, they could be measured parameters. They could also be derived from first principles. So it could be gray box, could be white box. Lots of variations here. If you look at not scalability, but actual performance or runtime, then if you look at loops, and most programs in computational science are composed of loops, then you may have come across the Roofline model for loop code execution. And the Roofline model says, if I want to predict the execution time of my program, I just have to take the maximum of 2 times. And the first is the time it takes to do the actual calculations, multiplies and adds. And the second contribution is the time it takes to transfer the data into the CPU and back out of it. And whichever of the two takes longer determines the runtime. Okay, this is called the Roofline model. And you may want to go to some more advanced modeling in this respect. So I will demonstrate later the ECM, execution cache memory model, where we also have contributions from data transfer and runtime. They're a little bit more evolved or complex. I'm not making assumptions here from the start about the overlapping. So it's a little bit like a generalization of the Roofline model. Okay, so in computing, we can have analytic models with white box and gray box behavior as well. Now here's an overview slide of the insights you get from different approaches to modeling. Purely predictive analytic modeling, so purely white box modeling, gives us direct insight into bottlenecks. Okay? We only use documented behavior. We only use stuff that is true, so to speak. And that's good. If the model fails, then the assumptions in my model are challenged, or the input data must be wrong. Okay. For example, the Roofline model gives us an absolute upper limit for the execution performance of some loop code. And if the measurement of the performance is above the Roofline model prediction, something must be wrong. Okay, that's very good because you have a definite upper limit. Now, refinements of the white box model lead to better insights. Okay, I can look closer. I can look more in detail at the hardware-software interaction and what's going on. Now, if I put in some gray box components, I call that a phenomenological analytic model. I do have similar insights as with white box models, but I have some uncharted territory. Okay, these gray box parameters, these measured parameters I put in, I don't know where they come from. Okay, I might have hypotheses, but ultimately I don't know. Now, the model failure points to inaccurate or unsuitable measurements. And of course, I have the same problems as white box. So I have to go back to the drawing board if something fails and refine my model. The curve fitting analytic models of the black box kind yields predictions. That's a good thing. Okay. It can be well automated. That's another positive point. But the failure of the model more or less indicates only the shortcomings of the fitting approach. Okay. I have to go back and see, okay, this was not the right fit function. Maybe I need more fit parameters. Maybe I need a deeper neural network, whatever fits the bill, okay? And the refinements of the model then consists of using a larger training set, using more fit parameters and such. So it's a different kind of approach. And here in this talk, I will concentrate on white and gray box modeling. Okay, now getting even more specific, I want to turn to resource-based performance models because white box is really a generic term. It couldn't mean anything. Okay, if I have a simulator that simulates my CPU and my memory to the actual transistor level, I have a white box model. It may not be useful in practice. It may be very slow. Okay, might not understand the results that come out of it. So I have to be a little bit more specific about what we want to know. So what's the question we ask when we do performance modeling? Now, the ultimate goal of modeling is to understand better what limits the performance and what can I do about it? Could I probably accelerate the program by doing some code changes? So the ultimate question is, how much of some resource or a couple of resources does the stuff that I run on the hardware need, and why? And if I get these questions answered, this question answered, then a lot of insight has been gained. Okay, and this leads us to analytic resource-based first principles models. Now, to make this distinction more clear, let me compare two different approaches to white box models in terms of computing. The first approach I would call mechanistic. Okay, the mechanistic approach thinks about execution of programs on computers as a thing that happens cycle by cycle. There's a little machine with lots of cogwheels, and it crunches your code, it crunches the data. Everything takes some time, but the time is like a latency. Okay, this unit takes so much time to do that, and then it takes the next thing and next thing and next thing. So the way we employ such models, such mechanistic models, is by means of simulators. I can have a simulator of my CPU, I can run my code on it, and the simulator tells me exactly which of those little cogwheels turns most slowly, or which is the culprit. Maybe it's very complicated and I don't see the actual reason for the performance as it comes out of the simulator. So the answer to most questions here is it's complicated. There may be cases where the simulator gives me a definite answer, but in practice, it's the case that the simulator gives me a prediction of runtime. I can use that to my advantage, but the insight may be limited because the simulator is such a complicated map of the actual hardware. Now, the other way of thinking is this resource-based approach I want to describe here. Resource-based modeling relies on the concept of resource utilization. Everything you have in a computer is a resource. You have execution units that can deliver results at a certain maximum rate. You have data paths that can transfer data at a certain maximum rate. Everything takes time, okay? And this time can be computed from the amount of resources you need and from the rate at which the resource can be provided. So instead of thinking about little cogwheels turning and little clocks ticking, we think about data flowing through the system, or work results being spat out at a certain rate by units that can do that work. Okay, and then the question is, all these things take time. All these resources take some time to do the work they are assigned with. So how do these different times overlap? So this is the most important question, as we will see. In order to make an actual problem manageable, to model an actual code running on actual hardware, we have to make simplifications. And these can be really, really hard simplifications. Just boiling down the whole hardware to 2 numbers, memory bandwidth and peak performance, as the Roofline model does. And it's still useful, although it's such a hard simplification. If it doesn't work, if it gives us bad predictions, inaccurate predictions, we can refine and iterate. And this may lead us to new insights. Okay, so let's talk about these bottlenecks. A computer consists, in this resource-based thinking, a computer consists of lots of bottlenecks. And I number them I, okay? Resource bottleneck number I. And each resource bottleneck can deliver resources, whatever it is, data, results, at a maximum rate, Ri max. Now, from each of these resources, the program needs a certain amount of resources, okay? From each of these bottlenecks, the program needs a certain amount, and this amount we call Wi. W stands for work. Work doesn't necessarily have to be actual work, like multiplies and adds. It also can be an amount of data that has to be transferred through some data channel. Okay, just the needed amount of resources. So here's my work, and here's my resource bottleneck, and I have to squeeze this work through the bottleneck. And the time this takes is easy to predict. Okay, the minimum runtime it takes for the work to go through this bottleneck is the amount of work divided by the rate that the bottleneck can deliver the resource. Wi divided by Ri max. There might be a latency component involved, but it turns out in practice, we don't need much of this latency component. We could put it in as a correction parameter to refine the model, but it's often not necessary. All right, of course, there are lots of bottlenecks on a computer. There's computation, there's data transfers, and not only one data transfer, there's data connections and data channels all over the place, okay? So the expected runtime is a function of all these times. Each of these times I can calculate if I just know enough about the hardware-software interaction. And the question is, what is this F? Okay, what does it look like? And if I get a hold on that, if I can make a good hypothesis about the F, how these different times block together to give me the expected runtime, I can very easily calculate the expected performance by dividing the overall work by the expected runtime. And the overall work, this can now be something that is very application specific, very near to the end user, like number of flops executed, number of iterations executed, number of letter side updates, and so on. So that's where the actual application work comes in. All the WIs down here, these are things that I can derive by careful analysis of the code. They could be different kinds of things, but the work here, this is actually the work that the end user sees when the program executes. Now let's have an example about this bottleneck model of computing. Let's simplify it very much. Let's say we have 2 bottlenecks only. We want to execute this OpenMP parallel loop, just making an array update. So I have to read C, I read A, and then write back A. The array length is 10 to the 7, so I have to get these arrays from and back to memory. Okay, let's say we have this machine. It's an N-core CPU. From the parameters, I can tell you this maybe one core memory group of an A64FX CPU as like the one in Okami. And then the maximum rate at which this thing can deliver results, floating point results in double precision, is 768 gigaflops per second. Okay, this is the maximum multiply AI floating point rate in double precision. And the maximum rate at which the data can flow through this bottleneck, the memory data path, is 210 gigabytes per second. So this is a first principles input. This is completely white box. The 210 is actually gray box because this is a measured value. All right, now let's calculate how much time it takes for these two bottlenecks, for these two resources to deliver the work they have to do. We have 2 times 10 to the 7 flops, and we have 24 times 10 to the 7 bytes to transfer. Now, to do the flops takes 26 microseconds. To transfer the data over this bottleneck takes 1.14 milliseconds. Okay. And the question is, how do these two things go together? What can I say about whether or not these two times overlap? Now, how do we reconcile these bottlenecks? We could have a pessimistic standpoint. Okay, if I want to have a pessimistic model, I could say all these times add up. Either I can do computation or I can do data transfer. Okay, or I could be very optimistic and assume full overlap. Anything that happens in computation can fully overlap with anything that happens on the memory interface in terms of data transfer. And this is actually what we call the Roofline model. Okay, the first reference I found on the Roofline model, it wasn't called that way at that time, but it is the model, was from Hockney in 1989, and Williams and co-workers have popularized it in 2008 and 2009, also adapted it to modern architectures in multicore. So the Roofline model for our example, of course, is 1.14 milliseconds. Okay, this is the larger of the two times. If I assume full overlap, it takes 1.14 milliseconds, and then calculating the expected flop rate, I can divide the amount of flops, which incidentally here is the same as one of our resources. I can divide that by the runtime, and that's 17.5 gigaflops per second. And that's what you measure, okay, for this architecture, for this machine, and this kind of code, it works very well. So this is Roofline thinking, two bottlenecks, flops, so execution units delivering multiply and add results, and data transfer. And it works for some kinds of code, of course. It does not work in other contexts. All right, so pushing this a little further, pushing the Roofline, the resource-based thinking a little further, we may think about other data paths in the architecture, or other things that can happen in the core beyond just executing multiplies and adds. And that's where the execution cache memory model comes in. It's a generalization of the Roofline model that takes multiple bottlenecks into account and looks a little bit closer into the architecture. So what it assumes is that we have registers on which, where there's a content in those registers, data, operands, and all the instructions of our program operates on data in these registers. And in order to do that, that takes some time. Okay, we call that core time. So the core time is the time it takes to execute a program, assuming that all the data is as close as possible to the registers. That means L1 cache. So with the core time, this can be quite complicated to predict. I mean, a core is a complicated piece of hardware, but it can be done in many cases. And then there's a data delay. It takes time to transfer the data from memory through the caches into the L1 cache and back. And all these data paths that are involved, like from memory to L3, then to L2, to L1, and back, all these data paths have a certain maximum transfer rate, maximum bandwidth. And then I have to calculate how much data actually gets transferred over these data paths, and I can calculate how much time that takes. Okay, so I get lots of predictions, lots of times. I get core time, how much time does it take to execute the program in the core, how much time does it execute to transfer data between L1 and L2, between L2 and L3 in memory, and I've got this collection of times. Okay. Now, if you want to know more about that and how it works in practice, how you can construct these machine models and application models and how they interact, there's a very extensive paper on that. The whole modeling workflow is not simple. Okay, it assumes you have to construct what we call an application model. It consists of course, the instructions, loop by loop, and problem sizes and other parameters. And we need a machine model. So, for example, how long does each instruction take? What are the latencies and throughput parameters of these instructions? What does the memory hierarchy look like? What are the bandwidth and latencies in the memory hierarchy and so on? And of course, the overlap properties. How do all these times overlap, which is highly architecture specific. And then you plug these together, and there's details here that I cannot tell you now. And in the end, you get a runtime prediction for a loop. And then you go to the next loop and so on. What people usually ask now is, can we automate this? Okay, can I just take my program, my full program, and put some tool to it and let some automatic mechanism do the work for me? And some of this workflow can be automated. Okay, we have two tools developed here at our group: Concraft, which does the whole modeling workflow, including data flow, and Osaka, which is a component of Concraft, and which does the in-core modeling part. So if you want to know more about that, I would be happy to answer questions or react to follow-up emails. All right, so now we have all these times, okay? By analyzing the program and the data flow through the architecture, we come up with predictions for each and every resource. And the question is, how do those interact? And depending on the architecture, they could interact in different ways. So here's an example for Intel, for an Intel Haswell processor. Most Intel processors are non-overlapping in terms of data transfers. What does this mean? If I line up all the data transfer times in time, so the memory L3 transfers, the L2, L2, L1, and all the transfers between the L1 cache and the registers, if I do this and I add them all up, I get the data delay. And all the other stuff that happens on the core, like arithmetic instructions, pipeline bubbles, waiting times, everything that pertains to code execution is overlapping. And in this particular example, data delay dominates. So this is the prediction of my runtime. It could also be that the overlapping part dominates. If there's some very expensive instructions in the loop code, like divides, or if I do lots of flops, like for trigonometric functions or exponentials, then this overlapping part could also dominate. Okay. So this is for Intel architectures. On AMD, we have a partially, or in case of the most recent architectures, fully overlapping cache hierarchy. That's why the AMD processors can utilize a lot of the maximum memory bandwidth, even with a single core. That's a really interesting and nice feature, as we think. So here we have partial overlap at the L2 cache, where the L3, L2 can overlap with L2, L1 transfers, for example. Intel Skylake, again, is non-overlapping, and it has this special feature of a victim L3 cache, which makes this thing more complicated to model. And here's the picture for A64FX on the FX1000 Fugaku supercomputer. It also has some mixed overlap model, where at the L2 cache, the memory transfers can overlap with transfers to the L1 cache at the L2 cache, while the L1 cache is not fully overlapping. So it's a complicated model. All right, so let's stick with the A64FX for the moment, because it's also interesting. You have an Okami machine, the Okami machine, which is similar to that, not quite the same, but similar. And let's compare the modeling prediction using the ECM model on this machine for different kinds of loop codes. And these loop codes are very simple. So here's a stream copy, here's a DAXB, you might know that from the BLAS library, dot product, initialization of an array with data, the stream triad, a sum reduction, just summing up the elements of an array, a Shinauer triad, which is like the stream triad with one more stream, and a 2D 5-point stencil in different configurations, which have different data transfer properties to main memory. And you see that in orange, we have the ECM model prediction, and in blue, we have the measured runtime. This is in runtime in cycles per vector length. One vector length on this machine is 8 iterations, so 512 bits. It's the vector length, and if I use a double precision algorithm that just access data linearly, then one vector length is 8 iterations. So you see in general, the prediction quality is very good. There's some discrepancy in some. And we see this also when we look at saturation. So here's again data for the stream triad, for the stencil code, and for the sum reduction. Now we start with 1 core and we scale up to 12 cores, which is the NUMA domain boundary for this machine. And we see for triad, the ECM model, which is the red dashed line, coincides with the measurements perfectly. For the stencil, we're almost there. So if you do a little bit of unrolling, which is necessary on this machine, then you get a very good single core prediction, and the saturation, at least you're within like 10%. And for the sum reduction, however, we're like 40% short of the prediction. So here something is wrong. And this is very interesting because this is a case where the model doesn't work. Okay, all the other kernels did work quite well, like triad and stencil, but sum reduction, even though it's a really simple kernel, it just sums up the elements of an array, but we're not able, the ECM model is not able to model this accurately. Okay, the prediction is optimistic by almost a factor of 2. So this leads us to the conclusion that something's wrong. And in this case, we have to conclude that, well, you have to go into the details here, which I can't, but let me just tell you that the add instruction on this machine has a very long latency. And this means that the machine has to overlap a lot of loop instructions to hide that latency, and it can't. It cannot do that here. The out-of-order resources on this machine are not sufficient to overlap all the instructions so that we get this discrepancy. So that's something we learned from a model failing. And we could put in a correction here, okay? But, well, the question is, do you want to do that? Just for this simple purpose of making the sum reduction model fit. All right. Now, these are simple loops, okay? Stream triad, 2D 5-point stencil sum reduction. And that's usually the type of criticism that we're up against. Can you do this for real code? Because these are toy codes. And the answer is yes, we can. Last year, right? Last year we published a paper. Actually, I referenced it before, where we just laid out all this modeling process for the ECM model, and the final application example was a preconditioned matrix-free conjugate gradient solver, which is not a really complicated program, but it consists of several loops back to back, executing on the hardware. And some of these loops are more complicated to model because they have internal dependencies, like the forward and backward substitution of the Gauss-Seidel preconditioner. And we did that on 4 architectures, AMD Zen 1, so Naples, Cavium TX2, Skylake, Intel Skylake, and IBM Power 9. And we were able to pretty accurately model the saturation property or the scalability of the complete code, the complete solver, using the ECM model. Okay, so that's in my opinion pretty interesting that this is possible. The downside is this is really complex stuff. You have to look into the details of the processor architecture, and it's really hard to automate that end to end. You can automate parts of it, like the data transfer analysis and data volume predictions, but at least for the initial contact with an architecture, it's mostly pencil and paper work. Okay. All right, so let me conclude with the node level part, the part where we deal with cores and sockets and NUMA domains and saturation. And let's go beyond the node level. Let's look at models for highly parallel code, or MPI code, for example, that could use MPI down to the core level, or OpenMP threads on the node level. Doesn't matter. And of course, you could make a simple assumption. The plausible assumption about a highly parallel code is that I have some execution time. Execution time means time that actually is spent in executing real user code. Okay, and there's some non-execution part, like time I spent in MPI libraries communicating or waiting for messages. It could also be time that's spent in an OpenMP runtime waiting at a barrier, things like that, non-execution stuff. And the plausible assumption about parallel programs is, and this is true for most programs in computational science, I have execution phases, I have communication phases or synchronization phases, and then there's execution phases again. They alternate. And the program should behave, at least if it's load balanced, should behave in a kind of lockstep pattern. So I'm adding the execution time to the non-execution time. So that's what my program might look like on two processors, T1 and T2. For the execution part, I could set up a model like the Roofline model. Okay, so the execution time is the maximum of the bandwidth time, transfer time, and the time it takes to execute the flops. Or I could use the ECM model, anything that works. For the non-execution part, if it's API communication, I could use something like the Hockney model. Okay, so transferring a message is latency plus data volume divided by bandwidth. And I could add these up. Okay. Now, if you do that for realistic scenarios, even if the load is completely balanced, so there's no option for like these two red bars or these two blue bars being of non-equal length, you see that this simple summation of times will not work usually. And it can go in either direction. So my prediction could be optimistic. The actual runtime is longer than my prediction. This is usually because I'm making too optimistic assumptions or too simplistic assumptions about these contributions. So my Roofline model might be too optimistic. It is optimistic by definition, so I might want to use something more realistic like the ECM model. Or my Hockney model is too optimistic. So this case is simple. Okay, I have just to adjust my models. But I said it could go in either direction. So the actual runtime of the program could be shorter than the predicted runtime. And this is really interesting because this is not really covered by my simplistic model. I think that this model should be purely optimistic, at least if I have an optimistic model for the execution part. Okay, so the point at which all this research started was actually a long time ago in 2004. At that time, we had compute nodes that looked like that. Okay, two single core processor chips sharing of a single path to memory, and one processor could already saturate the full memory bandwidth. And the second one didn't get anything, or just got half of it if you ran two processes on these two processors with memory bound characteristics. And at that time, I looked at MPI parallel lattice-Boltzmann solver. If you know lattice-Boltzmann, it's a fluid solver, explicit time-stepping scheme where we have compute phases and communication phases. It's a halo exchange scheme. And in the initial, when I looked at the trace, the timeline trace of this program, initially in the first couple of seconds, it looked like that. Okay, just the lockstep behavior we expect. Compute, communicate phases alternate. But then after some time, it turned out that the trace looked much different, and the trace evolved into this. So whenever one processor did work on the lattice-Boltzmann algorithm, the other one spent time in MPI, and then the roles reversed. So it's like some kind of alternating behavior on these two processes. And in the end, the runtime for this phase was better than for the first phase. So in the end, the performance was bumped up a little bit. So this program runs faster. Why does it run faster? Because the bottleneck is only used by a single processor at a time. Okay, so the average amount of memory bandwidth available per processor is higher in the second case. So this, as we call it, desynchronized state is faster than the synchronized state above here. So this looked like some kind of instability or snap-in behavior. Okay, so every computer system has disturbances or noise, and if you let it evolve a little bit, it wiggles a bit, and then suddenly it snaps into this non-synchronous execution. So this was very interesting. At that time, we didn't have the resources in time to follow up on that, and then came a paper by Markidis and co-workers in 2015, and they performed a simulator-based analysis on from a Cray machine. What they did, they injected delays. Okay, so they injected some waiting times into a parallel program, and of course, due to the dependencies implemented by the MPI communication, these delays propagate through the program, through the system. So here's the timeline plot of that. And what they observed is that an injected delay at some MPI rank propagates and then dies out. Okay, also a very interesting behavior. It looks like a wave, or if you want to call it a soliton or whatever it is, with some dissipative behavior. So there's some kind of mechanism that makes this wave disappear after some time. And at that time, they postulated a classical wave equation for a continuum description of a parallel program, and that was extremely interesting. Okay, they tried to describe the parallel program running on a parallel computer as a continuum, and these disturbances, like idle waves as they call it, they wanted to describe as traveling waves in this continuum. So extremely interesting approach. So it wasn't quite clear whether or not this phenomenon, traveling damped idle waves, and the previous one, desynchronizing behavior, had anything to do with each other, and it turned out they do. Okay, so here's what we started with. We repeated the experiment from 2004 on a more modern system. We ran a lattice Boltzmann solver on a system with 2 sockets per node and 10 cores per socket. What we see here is snapshots of timeline behavior for the first time step, the 20th, and so on, up to the 10,000th time step. For each MPI process, which goes down here, this is the rank from 0 to 99. For each MPI rank, we plot the point in time as a red dot, as a red cross, when this process reaches time step 10,000. Okay, and it turns out after some time, after some evolution, these MPI processes do not reach the same iteration at the same time. So some are faster. These are the speeders, so to speak, and there are some which are slower. And if you let it evolve for some time, you see that there's some wave pattern emerging. We call that a computational wave. The blue bar is the actual prediction from a simple additive model. So this program was faster than what the composite model predicted. And even more, it's not just that the processes overlap with each other, they overlap in a specific way. They form this wave-like behavior. And it's always a single wave. It's never like a more complicated structure. It evolves as a complicated structure, but in the end, it will always be a single wave. This, of course, is very similar to what we call spontaneous symmetry breaking in physics, because the whole program is symmetrical. Okay, you can shift the MPI ranks, you can renumber the MPI ranks, it's the same, but the evolving pattern is not symmetric under this transformation. So when does that happen? And is there instability? And is the instability always there? Does it only occur under certain conditions? So these are interesting questions. Now, it turns out that we can trigger this instability by the idle waves that Markides and coworkers have studied 6 years ago. And this is the connection between the idle wave phenomenon and these desynchronization patterns. So here's some research questions we have had to ask ourselves. So first of all, how do these disturbances propagate? Okay, if I inject a delay at one rank, and these are timeline traces here, if I inject the delay at one rank in my program, how will it propagate? Will it run into a boundary? Will it disappear? Will it wrap around depending on the boundary conditions? And how does it depend on the communication characteristics? Okay, does it make a difference if I only communicate with my next neighbor or next to next neighbor or further apart? And then how do these idle waves interact with each other? If I inject multiple idle waves, as we've done here in this experiment, we see that idle waves travel and they run into each other and they interact. And this is probably the most important insight from all this phenomenology. They interact in a nonlinear way. So when a large idle waves interact with a thin idle wave, they interact and the thin one dies out. Okay, so this is a nonlinear interaction. And this is one of the major insights. The medium in which these idle waves travel, if you want to think about it as a continuous medium, this medium is a nonlinear medium. And then we have decay of idle waves. And the decay of idle waves could come about in different ways. Okay, idle waves can decay just by interacting with the system noise, but the same mechanism, they interact with each other, they can interact with system noise, and so they decay. This is what Markides and coworkers have observed. But idle waves can also decay without any noise present. They can decay by interacting with system bottlenecks, like the memory bandwidth or the communication bandwidth. And then finally, if an idle wave travels and it dies out after some time, in some cases, a residual pattern emerges. So there's an echo of the idle wave. Even though the idle wave has run out, it had run into a boundary or it interacted with noise and it's eliminated, there might be a residual effect, which we call a computational wave. And this is what we show here. This computational wave means that different MPI processes arrive at the same point in the program at different places. And this state is stable. Okay, you can wiggle it a little bit, Maybe it shifts around, it maps to other MPI ranks, but overall the pattern is stable. And it turns out you only get this behavior, this snap-in behavior into a desynchronized state if a bottleneck exists in the program, like memory bandwidth or communication bandwidth. And then finally, and we're not there yet, can we somehow make a continuum description out of that? Could we transform all these microscopic insights that are based on how individual processes interact and how they interact with bottlenecks? Could we turn this into a mean field description, so to speak, in order to describe the whole thing as a nonlinear medium? Okay, I think I'll skip this. So here's a little bit more detail about how idle waves interact and how they interact nonlinearly. So in this experiment, we injected idle waves at regular intervals across ranks, and each idle wave was the same size to begin with. So we just injected a delay or some increased amount of work. And then since we have next neighbor communication here, the idle wave traveled away from this disturbance. And this happens for every one of these disturbances, and they run into each other and die out. Okay. By the way, these idle waves are not restricted to computation or parallel programs. You can also observe them in train schedules or flight schedules. If one train gets delayed and other trains have to wait, then you have idle periods traveling through your schedule. And this is exactly the same phenomenon. Okay, and then if you inject random idleness and you observe what happens, then these idle periods or idle waves, they travel and they interact nonlinearly. Now imagine that these small injections that we see here are not actually injections that we put in. They could be noise coming from the system. Noise from regular processes like cron jobs running on the system, noise from non-constant access to data, for example, noise from the network, because not every communication process takes the same amount of time. So all this noise can interact with an idle wave in this way, okay? And if you understand that, then it becomes clear what the reason is for the decaying of idle waves. And this noise-induced decay happens because all these noise particles in the system, all these delays, they interact with the trailing edge of the idle wave. And this means also that the actual statistics of the noise, so whether it's shot noise or Gaussian noise or white noise, doesn't matter. All that matters is what's the overall, the integrated power of the noise that interacts with the idle wave. And that's also a very important insight. Okay, the statistical properties of the noise do not matter for the decay of the idle wave, up to some scale of course. If the noise is just a huge one-shot injection, then it's different from statistical noise. But you can see this in experiments, and it's also clear from the microscopic mechanism of interaction that the statistical noise on your system does not matter if you want to describe the decay of idle waves. So this was one of the big research questions we had when looking at decaying idle waves. All right, so now approaching the topic of computational waves. So what is the echo that is left behind when the idle wave dies out? I told you that this echo persists only if there's a bottleneck in the program. And you can very easily make an experiment that shows this. So for example, in this case, we have a 10-core processor in our cluster, and we run a stream triad program. And if you run a single core in each socket only, we have a resource scalable program, because each core, each MPI process has a core and a full socket on its own. And this means there's no memory bottleneck. If you run such a program and inject an idle wave, it just runs into the boundary or runs into itself and it dies out. And there's no echo, okay? There's no computational load. And if you go up the scalability curve, this doesn't change. As long as the program is still scalable, as long as we're not in the saturated regime, we don't have any persisting echo of this idle wave. But as soon as we approach saturation, we see that even though at a point where the idle wave has died out, we have some shift in the time when certain processes enter a certain phase in the program. And if we go to full saturation, we'd use 10 processes per NUMA domain, so full saturation on the socket. We see that even after the idle wave has run out, we have an echo in form of the computational wave. We have processes here in the middle of this socket, which finish the program considerably faster than everybody else. Okay, and this is because the communication times and the computation times on the socket can overlap with each other. And in the end, if you count the number of processes active at the same time on a socket, it's pretty exactly the number of processes you need to separate the bandwidth. This is also a major observation, that the system seems to settle at a stable point where just enough processes run on a socket to make the memory bandwidth separate. Okay, and the question is that a general law? It's not. You can measure that. Okay, if you make a more complicated communication pattern, not next neighbor, but next to next to next neighbor, and so on, then the system becomes more stiff, and the number of processes active at the same time rises. So there's more phenomenology here that we still have to explore. Now, if in such a desynchronized program, computation and communication can overlap, the question is, can I use that to my advantage? Can I take a load balanced program, a perfectly load balanced program that runs in lockstep, and let it evolve, and then just due to the presence of a bottleneck, have some automatic overlapping of computation and communication? And the answer is yes, you can. Here's an example of a Chebyshev filter diagonalization application, ChebFD. There's a paper on the details from 2018. And what it does is it calculates a part of a spectrum of a huge sparse matrix, of a Hamiltonian matrix from quantum mechanics. So that the goal is to compute the density of states in a part of that spectrum. Now, this program is hybrid parallel. So you can run it with pure MPI or with MPI on top of OpenMP threads. So there's a choice that you have what you do with the cores on a processor. You could run a team of threads on one processor and have just one MPI process. This forces all the cores on that processor into lockstep because you have these OpenMP barriers that synchronize the threads. Or you could use pure MPI or multiple MPI processes per socket at least, which would then constitute a bottleneck across these MPI processes. And well, if there's considerable communication overhead, what we expect is that if there's a bottleneck, if there's more than one MPI process per NUMA domain, then the desynchronized program should be faster. And in this program it was a desynchronized program running one thread per MPI process, 10 MPI processes per NUMA domain. This is a timeline plot. And in this situation, the code was 6% faster than the lockstep code with 10 threads per NUMA domain. So this proves that even in realistic scenarios with realistic code, this desynchronizing behavior can give you a performance boost because there's automatic overlap. And then you can go one step further and can ask, can I provoke that? Okay, in a program that has lockstep, can I provoke this behavior from the beginning by kicking it, by injecting a little delay in one process, letting it progress through the system, and then forcing the formation of idle waves? And the question is also yes, you can. Okay, now here's some results. I will not go into all the details. If you're interested, I'm more than happy to answer questions. So the instability of bulk synchronous programs that do not have any interior barriers in unit synchronization is bound to the presence of a resource bottleneck. You need a resource bottleneck like memory bandwidth or also communication bandwidth in order for the lockstep state to become unstable. This means, for example, in terms of memory bandwidth, if you run one MPI process per socket in your program, you will not have a bottleneck in this respect. At least not in terms of memory bandwidth. So such a program will always be automatically synchronizing. These desynchronized programs could exhibit automatic computation overlap. Okay, I can hide my communication behind data transfer to memory, which is a good thing. Idle waves can be used as like a trigger for these computational waves. I can inject an idle wave, and then the idle wave runs out by whatever mechanism. And in the end, all that's left is a computational wave in a desynchronized execution. Idle waves decay via different mechanisms like topological noise or system noise or interaction with other idle waves. The noise statistics is irrelevant for the idle wave decay rate. This is very important. And we have an analytic model actually for the idle wave velocity. So we can say, depending on the communication characteristics and the mode of communication that you have, we can exactly predict how fast the idle wave will travel for the scalable case, not for the non-scalable case. There is experimental evidence, which I haven't shown here, but which is in one of our papers, that major question. Okay, that's also one major question. If I have a program that has MPI collectives, do the collectives destroy this this desynchronizing behavior? Do they destroy the computational waves or the idle waves? And some don't. You can show that depending on the implementation. Okay, what's future work? We want to develop a comprehensive simulator framework that can enable us to study these effects on a much larger scale. Of course, you don't want to run these programs which essentially do nothing on a huge supercomputer, burning cycles that other scientists could use to their advantage. So we in the process of developing a simulator that can help us explore more of this. We have no analytic description yet for decaying idle waves if there are bottlenecks present. We could explore bottlenecks other than memory bandwidth. Irregular programs are a challenge. Okay, we always assume this implicit lockstep behavior. There's no load imbalance. What happens if the program has an inherent load imbalance? Can this whole phenomenology also help me get a speed up by overlapping? And then there's some more far-reaching research, like could I describe the processes in my program which alternate between communication and computation phases? Could I describe them as oscillators? Because it's oscillating behavior, okay? Compute, communicate, compute, communicate. It's like an oscillator. And there are lots of models in physics that, and solvable models also, that have this behavior, coupled oscillators that show collective behavior. And one of the most prominent models is the Kuramoto model from the 70s. And we have shown that we can establish a modified Kuramoto model that shows some of the behavior in a purely physical setting. So we can describe coupled MPI processes using coupled oscillators using a certain interaction potential and recover some of that behavior. And then finally, of course, as I've indicated multiple times, there's still the search for a continuum description. So could we somehow describe a parallel program running on a parallel computer as a continuum? And could we describe the disturbances you observe, idle waves, computational waves, as nonlinear waves traveling through that medium? Thank you very much. And I'm happy to take questions.
Okay, thank you very much.
Was my sound okay? Because I got warning messages about my microphone. Okay, good.
Loud and clear almost all the way through, so yeah. The internet has served you well today. Let me start the questions off. Obviously, people should either speak up or type them into chat, but how this synchronized waves of idleness and behavior patterns is very interesting. I've not seen such a clear in-depth discussion before, so it's very valuable. Clearly, lots of us have both synchronous applications, and how beyond the mechanisms you've spoken about, how else to mitigate it? So, for instance, how does over-decomposition play into this? So basically, assigning to each process multiple physical domains to compute on, so that in order to get better load balance and work distribution.
Well, actually, that's a very important question. So is it actually always necessary to load balance a parallel program? Because if you have desynchronization anyway, and if it doesn't hurt, or maybe it even is beneficial for the performance, maybe I can get away with not load balancing my program, because all the little differences in execution time on the different processes, they could overlap with communication or with each other, in the end leading to better resource utilization. So we're in the process of investigating that. That's an interesting question. And we're in contact with groups that do research on load balancing algorithms and how we can reconcile that. And the honest answer is, I don't know, okay? I don't know if it's probably there's a scenario or there's a corner in the configuration space of all possible parallel programs where this load imbalance doesn't hurt me, but is actually beneficial. Yeah, very good question.
Okay. Let me jump in with another question, since people seem to be shy today. You use Blackbox to describe one of your modes of performance modeling, but Blackbox sort of has another meaning where you don't get to look inside the black box, right? And so often we're presented with large, complicated applications with multiple kernels. And I know Ava's grappling with a couple of these right now, and yet you have to do something to understand their performance, right? So, and do something to improve it.
Yes. So of course you can, if there's two ways to approach this. If you approach performance as a research topic, then you start with something simple and you make it more complicated. That's what I described basically when we ended up with this preconditioned CG where we showed that it works. Okay. The other direction is if you approach the topic as a kind of performance analyst or performance engineer that has a program to analyze that they haven't seen before. So they don't know what loops it comprises and what resources are actually needed. So what we do is we measure, and that's pure black box strategy. Okay, I measure what's going on. I try to find the characteristics of a program, but still you can get very quickly to the white box thing, because what do you measure? You measure bottleneck utilization, like memory bandwidth utilization, or is your ad unit utilized fully, or is the load balanced? So these kind of things, you measure the kind of instructions executed. And then you get, of course, you break that down to the subroutine and to the loop level, and you get very quickly to the point where you look at a hotspot. You already know, because of your measurements, what makes that hotspot tick. Maybe there's a load imbalance, maybe there's a scalar execution instead of SIMD, and then you get onto the other side of the river and say, okay, let's make an analytic model out of that. Of course, there's the gray area in between where it's so complicated that it's just not possible to do that. And we encountered that when we cooperated with people from the Blue Brain project in Lausanne, in Switzerland. They have very complicated kernels, which comprise lots of flops, but also divides and exponential functions. And it turns out that the models we have are not fit for that. So all we could do is look at critical path lengths, and we could see, okay, the execution time is somewhere between the critical path of the kernel, so the longest time it takes to go through all the instructions, and the optimistic assumption of full throughput. But between that, you would need a lot more insight. You would need something similar to a simulator to really understand what's going on. Okay, and that's where probably curve fitting models and black box models help you get further, because you can get predictions without actual insight. I'm not trying to bash these black box models. I did that for some time, but I see the benefit of that. And sometimes you can't get further without that.
Yeah, they're essential starting points in many settings, but then we have some application developers on the call. Is everyone's application running at full speed?
I can ask, can everybody raise a hand who has ever come across the Roofline model, or even used it in their analysis or in assessing the performance of programs? Has anybody ever used the Roofline model, or at least? Yeah, of course.
There's some names on the call that I know must have used it, so but that's
in our group, so.
Can I ask a question?
No, go ahead.
Yeah, so I really enjoyed the talk. I really like the physical. So I'm a quantum chemist and do some high performance computing, and I really like the physical analogy. And I'm just wondering how, so you spoke mostly about sort of a computer cluster environment where I guess there's some, you can almost think there's some notion of like physical distance between processes. Is that the right way to think about it? And then how far can you push the physical analogy? Like we do a lot of GPU computing where there isn't really this notion of physical. I'm not sure exactly how to ask the question that I'm trying to ask, but I guess how easy is it to push this physical analogy to other sort of parallel architectures, I guess is what I'm trying to ask.
Okay, so it's not so much about the the physical distance in the cluster. It's really about the dependencies here. So the distance of one process to another is defined by how long it takes to communicate with that process and by the sheer presence of a dependency. So in a real program, you have one process communicating with a collection, usually not all, hopefully, other processes. And these dependencies, they define the communication structure. We can describe that as a topology matrix or communication matrix in the program. And you have that in any highly parallel program. And this is what basically defines the general behavior of the medium, if you want to call it like that. So if you have long-range communications or communicate with a lot of partners, everything you do, every disturbance that you put into that program travels very quickly because you cover a lot of distance in a short time. Okay, if your longest distance communication partner is very far apart, then it just takes you a couple of hops to cover the complete program and then probably wrap around. However, if you have truly local communication, only next neighbor, for example, then it takes a long time for a disturbance to travel. And it's like if multiple trains are waiting for your train or just one train, okay, the phenomenology is totally different as an impact on the schedule. So this is what defines the relationships, not physical distance, but communication properties. And the second thing, that the fact that it's actually communicating makes it a dependency because the other process cannot go on before it has received that message. So communicating with a lot of partners makes the whole system stiff, okay? It's like if you communicate with a lot of partners in every step, it's like a little bit like putting in a barrier after every step. And all this phenomenology just goes away if you have too many partners. And the second thing that comes in is the duration of an individual communication of a message. So latency plus volume divided by bandwidth. Because if you communicate longer, if this takes longer, it gives you more opportunity to overlap with it. So in a program that does communicate, but only communicates tiny bits, and the latency is really just a microsecond, and then you compute for a second, all this is more or less unimportant because there's nothing to overlap. Also, if you have a program, well, okay, let's stop at that. There's another scenario that we also investigating right now is when you have programs that alternate between memory bound, so bottleneck prone code, and completely scalable code. Like something like that happens, the sparse matrix vector multiplication, which is really memory bound. And then you do some in-core computation, some exponentials or whatever. And you have these alternating phases. Then even without communication or without significant communication, you could also desynchronize these phases and have the processes on one socket execute, half of them execute the bandwidth bound part, while the other half executes the core bound part. That will give you a benefit, of course, even though there's no communication component to overlap. You overlap useful work with useful work. So it's really about what you do. And if you talk about GPUs, of course, then the problem is that on a GPU, usually you run a single kernel only. Nowadays you can also run multiple MPI processes on GPUs, but if you run a single kernel, a single process only, this is a scalable resource. If you take two GPUs, all the bottlenecks multiply. So you have a scalable program. The only bottleneck that could come in is in the communication. Okay, if you have bandwidth bound communication, then you have a bottleneck to desynchronize on. But for memory bandwidth, it doesn't count. Of course, this changes if you have multiple MPI processes per GPU, and that's also a future direction which I haven't mentioned here that we're investigating. Very interesting.
Yeah, very interesting. Yeah, thank you very much.
Have you looked at some of these same concerns in the context of data flow programming models or dependency style programming? So we're in the process of moving, well, for one of our main programs, Madness, from a sort of something that is sort of bulk synchronous style into something that is basically task-based execution with the dependencies managed sort of semi-explicitly on a sort of like a DAG. And we're actually seeing more variable performance than we were expecting. And so we're still trying to get to the bottom of what causes that. But I mean, looking at the behaviors that you were seeing, it's entirely possible that some of these bubbles are popping up, and the we're not sticking closely enough to the critical path or something?
Really hard to tell without looking at the details. Usually I would say that if you take out the bulk synchronous part, if you let if you let things run more freely without mutual synchronization, then there should be more opportunity for overlapping. But it depends on where you are in the configuration space. As I said, if there's no significant communication overhead, there's nothing to gain. If you do work all the time, there's no way you can do the work faster, okay? If you're bounded by some bottleneck or by computation. It's only where you can overlap different work characteristics or work with non-useful time, like communication, where a benefit comes in. So you would have to look at very specifically what case you're looking at. And it could entirely be that the same program with a different input data set could show completely different behavior in terms of desynchronization and computational ways.
Very good. Thank you very much. Any more questions from the audience? Then I think we should thank you, Georg, very much for his time. It's in the evening there. We've probably imposed on his dinner time. And so thank you very much. And
welcome. Thanks for having me. It's very nice talking to you.
Thank you. Bye-bye.
Bye.